welcome to this lesson of industrial automation and control. Today we are supposed to do lesson number 10, but because we could not complete one topic in lesson number 9, which is very important in instrumentation, called phase sensitive demodulation. We will just take a few minutes to cover the topic first and then go into lesson number 10. So, we start with lesson number 9, the next part of that. So, lesson number 9 continued, lesson number 9 was on signal conditioning. So, we straight away come to phase sensitive demodulation, and let me try to explain this, because this arises in many different sensor applications. So, first of all, let us realize that from many sensors, let us say we have a capacitance sensor. We have just seen in our last lecture that capacitance sensors are often the signal from capacitance sensors, which in capacitance sensors there are the capacitance gets modulated by the quantity which is measured, suppose motion, right. So, now this change in capacitance, which is typically we have also seen that typically there are two capacitances, and if one capacitor becomes C naught plus delta C, the configuration is made such that the other capacitor becomes C naught minus delta C. So, that we have seen that typically if you have two fixed plates and if you have a parallel plate in the middle, so then and you have terminals from here and here and here. So, you actually form two capacitances, and it turns out that these plates are fixed and this is the movable plate. So, obviously, if as long as the displacement is small, we can say that if this C1, both of them are actually equal, because in the nominal position the separations are equal. So, if it is C naught, if it becomes C naught plus delta C, if it moves to this side, then this one will become C naught minus delta C, right. And then these, so these two capacitances are typically, we have seen that they are formed as two ratio arms of a bridge. So, one capacitance is here and the other capacitance is here. So, this becomes C naught plus delta C and this becomes C naught minus delta C, and these bridges are actually excited by AC sources, right. So, okay. So, what happens is that now we see that the output becomes modulated, that is, so if you take a bridge and if you take the signals from here, what shall we see here? So, obviously, this excitation is generally of high frequency, typically of the order of, let us say, 2 to 5 kilohertz or even sometimes a little more. On the other hand, this motion is typically any motion will be of the maximum, let us say even if you take vibrations, even if you take vibrations, it will be of the order of tens of hertz or maybe 100 hertz. So, what is going to happen is that generally you have the output is actually a sinusoid of frequency 2 to 5 kilohertz, while the amplitude of this sinusoid is going to vary according to the motion. So, what you get is actually an amplitude modulated signal. So, you get, so if suppose the plates are moving like this, then what you will the output that you will get will be somewhat like this. Actually, the frequency I am drawing, because I cannot draw such a high frequency. So, therefore, and here there will be actually a phase inversion, because the modulating signal is negative here, right. This here the modulating signal is positive, the motion, here the motion is negative. So, therefore, there will be a phase inversion here, which will be very difficult to detect. These waves will actually look very similar if you see them in the CRO. So, it will be very difficult to detect whether the motion was, let me use a different color. So, whether the motion was like this yellow line or whether this motion was like this, would be like this pink line. both waves will actually look similar in the output, while the motion is completely different. So, therefore, one has to find a mechanism by which these motions can be separated, and in fact this that is the phase inversion here has to be captured. So, the demodulation mechanism, if you just put a rectifier, if you just put a simple rectifier, suppose you want to rectify this wave, then that rectifier will not do, because it will rectify both of them in the same way. So, it is not phase sensitive. So, therefore, we have to have a means such that we have a phase sensitive demodulator, which will sense whether there was a phase inversion here or not. Then we will be able to distinguish between this pink and this yellow kind of motions. So, this is the basic problem of phase sensitive demodulation. Now, so suppose, let me use a different pen now, because we have got a different background. So, typically suppose the motion xt is the actual motion of the plates. Just giving you an example, exactly similar thing will happen for LVDTs, which is an inductive sensor and where the core will move. So, the modulated wave let us say the xmt, which you will get out of the bridge, will be some a sin omega c t. This is the carrier wave, this is the excitation frequency, into xt, right. Now, from this xmt we need to get xt out, right. So, one of the strategies, there are actually various strategies. So, one of the strategies would be to multiply xmt. If you multiply xmt by again sin omega c, then suppose we multiply it by b sin omega c. Then this will be ab sin square omega c into xt. So, sin square omega c, so it will be ab by 2 into 1 minus cos 2 omega ct, right, xt. So, we will get one signal which is ab by 2 xt and another signal which is ab by 2 xt cos 2 omega ct, right. Now, you see omega c itself, suppose xt is low frequency signal motion, so about 5 to 10 hertz, and omega c is let us say 5 kilohertz. So, there is 1000 times separation and 2 omega c is 10,000 times. So, you naturally see that this signal will be, this will be a 5 to 10 kilohertz signal, 5 to 10 hertz signal, because it is just xt, while this it can be shown easily that this will be a signal which will stay very close to, whose components will stay very close to this cos twice omega c, namely of the order of 10 kilohertz. So, we need to now separate. So, now the signal, this signal is actually a sum of a 0 to 5 hertz signal and a 0 to 10 and a signal which is around 10 kilohertz, very narrow. So, it is very simple to separate these two. Any simple low pass filter will, since there is so much separation, will actually cut off this 10 kilohertz signal and will give you the 5 hertz signal, which is this xt. This is the basic principle of phase sensitive demodulation. So, exactly this is what is being done here, that is so you see that this is the signal which is a modulated signal from the bridge, let us say, or from an LVDT, and we are multiplying it by the same sin omega naught t, where sin omega naught t is either the primary excitation frequency of the LVDT or the excitation frequency of the bridge. So, we are multiplying it, this is a multiplier like I did, and then we are low pass filtering it. So, if we low pass filter it, what we will get is a signal which is proportional to the original motion signal. This is one way of, this is conceptually the simplest way of doing phase sensitive demodulation. Now, this multiplication is not such a simple thing to realize. So, therefore, there are various other lower cost simpler circuit versions which will also realize this, they are also in a sense like multiplication, but not exactly. So we will see some some realistic circuit. So for example, let us see this one. So you see this is a simple phase sensitive rectifier. So here we are using a rectifier, but it is a phase sensitive rectifier. So how does it work? I don't know. Okay. So you see what is happening here. First of all, let us realize that this is the low pass filter. That is something. What is this? This is a summing amplifier. Yesterday we have seen summing amplifiers. For this path the gain is 1, it is R by R. For this path the gain is 2. So it is actually, if you call this as V1, if you call this as V2, then Vz is equal to minus of V1 minus of 2V2. Now you see that what is this? This is a simple unity gain inverting amplifier. So the gain here is minus 1. So here at this point of time, this V0 dashed is equal to minus V0. This is the signal that we want to demodulate, right? Now here is a switch, and the switch is synchronized. How it is synchronized? That suppose whenever this signal is going, so here you have V1 equal to V0 dashed is directly connected, and here this minus V0, so this is V and this minus V is being switched on and off. So suppose we switch it in such a manner that when V is positive, this switch is on. So when V is positive, this is minus V, or rather maybe when V is negative, okay, suppose when V is positive this is off, and when V is negative this is on. Okay, so this V, so when V is positive, first of all this is off, so therefore the signal is, so now imagine that V is something like this. So we have got a picture of this. So let us just imagine that the input here, this input is, let us see that signal, then we will be able to understand better. Suppose the motion is like this, right? So it stays positive, then goes negative, then it goes positive again, then it goes negative and stays negative. Okay. Now what is the phase, what is the amplitude modulated signal? So you see that for some time the amplitude is remaining constant, then the amplitude is actually decreasing, that is the linear part. Here it is going negative, so there is a phase inversion, and then the amplitude is increasing negative, and then for some time it is remaining constant. So this is the wave. The carrier frequency is shown to be much smaller because then the picture will become cluttered, but we can imagine that actually the carrier frequency will be much higher than this, but the waveform will be if you draw the peaks, then it will resemble the motion, and since here there is a phase inversion, so therefore the motion will be negative. So this is the modulated wave which we have to demodulate. So we go ahead. Now you see what's happening to this circuit. So you see, suppose the switch is, in this case they have assumed that when the switch is closed when positive, so when it is closed when, so first of all you see when it is open, then Vz equal to minus V1 minus 2V2, and V2 is 0 because the switch is open. So therefore this is just minus V1 Vz. So therefore the negative half, actually the wave was like this if you recall. So the negative half, so Vz will go up, it will be minus V1. On the other hand, when the switch is closed, then what will happen? So when the switch is closed, then it is minus V1 minus 2V2, So, and V2 is equal to minus V. So, it is actually it is going to be minus V plus 2V. So, is equal to V. So, when it is positive, then it is plus V, when it is negative, then it is minus V. So, negative minus of negative means positive. So, essentially the wave will be rectified. So, now you see that is why you are getting this wave. So, it is a full wave rectified wave, but when this V will itself go negative, then when V will itself go negative, so you can see that it is always when it is closed, then it is V. So, now when V is going negative, so actually this wave is being synchronized along with the sine wave. So, the carrier sine wave. So, when the carrier sine wave, so now when it is now closed during the when the wave is negative. So, the same thing is happening here. It was closed when the wave is positive. Here it is because there is a phase inversion, but the sine wave carrier is still positive here. So, therefore, the switch becomes on. So, the switch gets on and off according to the carrier wave. So, then we will get a, so you see that when there is a phase inversion, the signal goes negative, it's rectified, but it's rectified in a phase sensitive manner. It's not an ordinary rectifier. Now, if we send it to a low pass filter, then what will happen is that simply these you will get the envelope of the wave. So, if you get the envelope of the wave, then you see that you are getting back the motion. So, this is the basic principle of phase sensitive demodulation, and it is applied in various large types of inductive and capacitive sensors. So, now having said this, we can now get on with the measurement, our lesson 10, which is on measurement, noise and errors. And first of all, we will see the instruction objectives. So, the basic instruction objectives are that the student is able to describe the mechanisms of noise coupling. This is very important to understand that how noise is coming into this system. Then learn the basic principles of noise reduction, thumb rules, then one has to understand what are the error models of instruments, how the instrument errors are mathematically characterized. If you connect a number of instruments together and if you have individual specifications for them, how do you know the characterization of the propagation of error through instrument subsystem. So, if you typically it happens that you are connecting a number of individual components, each of them have some specifications of the manufacturers. So, one needs to understand that what is the overall specification of the instrument, because one has to understand that this instrumentation is very much connected to product quality control, and it is because it is either directly it is used to a large extent in quality control, product quality control, sometimes in product process and in product process control. So, in both cases the instrument accuracy affects the quality of the product, because if the process control is not well maintained, then also quality of product will suffer. And on the other hand, during inspection you directly observe the quality of the product and you either accept or reject the product. So, it is very important to understand the kinds of errors that the instruments are likely to have, and then accordingly decide what kind of instruments to buy, or what should be a good what should be a good interval for calibration of the instruments, etc. So, we first try to take at noise, the concept of noise. Noise can be noise in circuits can be generated in many ways. Sometimes it is internal, sometimes it is external. Internal noise, there are various descriptions of noise, but they are actually arise because of various atomic and molecular phenomena. For example, there is thermal noise, which is basically caused by the temperature induced electron motions. One can do nothing about it. Thermodynamically this noise will be there unless you probably keep things very close to the absolute zero, but that is not possible obviously. So, and then there are other kinds of noise. For example, in transistors and semiconductor you can have short noise. So, we will not focus so much on these kinds of noises, because firstly they are kind of inevitable, and secondly their levels are not that high. In fact, these noises are very important for very low level measurements, but much more important and much more strong noises can actually come in from various external sources, and they are also relatively easier to prevent. So, the three major sources of noise are actually noise that comes in from electromagnetic interference by inductive coupling from a noise source, and or comes through electrostatic basically electromagnetic interference are created by inductive coupling created by other devices which are carrying heavy current. They are it's magnetic, so some flux has to be created. So, for that purpose current must be flowing. On the other hand, electrostatic interference are caused by capacitive couplings. So, they are essentially caused by voltages and electrostatic coupling between from other high voltage conductors. And you can also have resistive coupling by one of the main reasons is that you can have improper ground connections in circuits which will cause ground potentials, and since all signals are actually reference to ground potentials, so therefore these signals will also become noisy. So, you have inductive, capacitive and resistive couplings, and we will take a quick look at these. First we take a look at ground loops. So, this happens when in a circuit you connect you have multiple grounds at multiple points, and not only have you have multiple grounds, these grounds. So, if whenever you have multiple grounds, there can be certain difference in potentials of these grounds, and not only that, these grounds may be connected, may be conductively connected, that is the resistance between these grounds may not be very high. So, in which case you have an equivalent circuit somewhat like this. So, you have the same circuit, this part is locally grounded at this point, this part the source is locally grounded at this point. On the other hand, these two potential there exists a certain amount of ground potential and they are connected by impedances. So, what happens is that you have ground loops. So, obviously currents will start flowing across this loop, right, and not just along this loop. So, naturally there are going to be voltage drops because of this ground loop current, which is not related to the signal at all, which is caused by this voltage source. So, this ground loop currents can cause potentials here, and if you are, especially if you are making single ended measurements, typically you will find that sometimes people will assume in a single ended measurement, we assume whenever you talk of a voltage is actually between 2 points, but sometimes we assume that one of the voltages is actually some standard common reference voltage of the whole electronic circuit, and to reduce, whenever this assumption is reasonably good, we can just take one of the wires and connect it to the circuit and assume that the other is the common ground of the circuit. Such measurements are called single ended measurements. So, you can see that when you make single ended measurements here, because of these ground loops you are going to get errors. So, that is why for more accurate measurements we must make differential measurements, where we are going to take both of these, and then some of these effects will actually go away, but still some of the effect can also be there, because there are going to be some current flowing through this path also, right. So, but in general differential measurements where you take 2 points and both wires are actually fed are generally more accurate. So, in other words, this is one of the problems where you have multiple grounds which are connected by not so high impedance paths, and where there is a difference between the ground potentials. There is another classic case of where you tend to get ground problems, and this happens in instrumentation a lot, because I don't know why this is going away. Okay, so so what happens here? Look at this. So, you have This is a very typical scenario in instrumentation, that you have some precision analog blocks followed by a digital block. So this is a very common situation where, you know, normally we go for high level of integration. So you can have some digital circuit switches, you can have some processor driven some small digital circuits, maybe ASICs on the same board. And suppose for ease of PCB layouts, you have connected the grounds. This is the ground point of the analog circuit block, this is the ground point of the other analog circuit block, and this is the ground point of the digital block, and they are on a PCB there are different parts. So you tend to think that the ground point of the rightmost part, and you have some point where you have a ground connection, so you have to bring the ground here and all the way. So you tend to think that if you are connecting, anyway you are connecting one point, anyway you are connecting this point to ground, then it is easier to connect the ground of this to the ground of this rather than all the way to the different ground. That will help will ease your PCB layout, but it will cause tremendous ground problems because of the fact that these digital circuit blocks are highly switching, and when they are switching, the power supply currents drawn which return to the ground are suddenly rise, and they are very spiky, and so you all the time you have this sharply varying power supply currents in these circuits. Now since these grounds are common, so you see that here the current Ig3 is flowing through this R3, the same current Ig2 plus Ig3 is flowing here, and Ig1, Ig2, Ig3 is flowing through R1. So if suppose Ig1 is actually a highly spiky current, so then this potential is going to I'm not able to bring this here. Oops, I got it. So the potential here, so if you have a very spiky current in this because of this Ig1, then the potential here is also going to oscillate, and obviously the potential here is going to oscillate, and the potential here is also going to oscillate. So at all the analog circuit grounds you are going to have an oscillating ground potential. So which will be, if you are making a single ended measurement, then this is going to induce noises here. So this is a basic problem of sharing a ground. Actually the right way of doing it is the following. So here you see this is the digital block, this is analog 1 and this is analog 2. So the right way of doing it here is to draw separate wires which do not share and then connect it to the ground using a solid very low resistance connection, only one of them, and very low resistance connection. So even if ideally if you have a short, then even if this current is switching, this potential will not switch, will not oscillate. So therefore you are going to have stable grounds at these points. So the whole basic idea is that first of all these ground resistances must be kept as small as possible, and secondly they should be connected separately using and then connected to a solid ground. This is one of the reasons why you see all the time that the ground planes are use thick conductor on the PCB layout. So next we talk about electromagnetic coupling. So in electromagnetic coupling what happens is that so here is a power circuit where high current is flowing. So this is creating flux. The same flux is actually linking this loop, which is a signal circuit where maybe we are trying to measure some voltage. So because there will exist this flux produced by this will be linked by this coil, which means that there will exist a mutual inductance between these two coils, and therefore some because of MDI/dt there will be some series mode voltages induced. So especially when you draw long wires and power supply wires are all the time running, and you are drawing a lot of power from these, so you have high frequency means about 50 hertz high current circuits. So they can induce quite a lot of voltage into these coils. So now apart from the, so now there are various options. For example, you can try to magnetically shield this these circuits, but that may be quite expensive. So one of the ways that is why one of the ways is that whenever we transmit, it is much more, if you transmit in terms of current, if you transmit our signal in terms of current and not in terms of voltage, it becomes much more immune, right. So we see that. So first of all, if you want to do, before we discuss that, first of all the first thing that you have to do is that you have to see that very little flux is linked from other from other sources. So flux linkage, if you want to reduce, you have to reduce the area of the loop. And not only that, it turns out, so you have to keep the coils close, and not only that, we know that if we twist the coil, so you have a twisted pair of wires, then what happens is that, for example, you see this is one leg xy and this is another leg yz of the same coil. Now the EMF which will be, if you have flux going up from here, then you can apply electromagnetic laws and can deduce that the EMF induced in Vxy is suppose going to be positive, so in this direction, and the EMF induced in Vyz is going to be in the opposite direction. So the effective EMF which will be induced by these such stray fluxes flowing, which will be linked by this coil between these 2 points, will actually be cancelled by in these successive loops. So what happens is that the net EMF which is linked by interfering sources is much reduced. So first of all, your area itself is reduced because they are twisted, and secondly, so very little flux is linked, and whatever is linked, whatever effect it produces, that also gets cancelled because of twisting. So this is one of the tricks that one can do, and the other one is that we can use current sources. So the other rule is that you must keep as much distance as possible from these sources of interference, because the coupling strength is going to reduce with the distance. So the distance should be as large as possible, and areas of conductor loop should be made small, and they can maybe even cancelled. Now this is an example which shows how, for example, suppose this is a series mode voltage induced by, let us say, an inductive effect. So if you have this E Thevenin, normally what happens is that the source impedance is much smaller, that is this Z Thevenin is much smaller than ZL. So you see that the EMF which is so if you have a series mode voltage here, then the whole series mode voltage will come and appear at the load. So whatever gets induced here gets transmitted to the output, right. On the other hand, if you see a corresponding current source, so here we have a current source, and for this current source, as we always know, Zn is going to be much larger than ZL, right. So it turns out elementary circuit analysis will tell you that the EMF which is induced, that is the output voltage, is going to be INZL, which is supposed to be the INZL is actually nothing but E Thevenin. So that is the open circuit voltage, which is the ideal voltage which should come, and the effect of the series mode resistance will be multiplied by ZL by Zn. So now since Zn is much greater than ZL, so this effect is going to be negligible. So this is one of the reasons why this 4 to 20 milliampere current standard has been so popular. So it makes a lot of sense to transmit instrument signals in the mode of a current. However, although nowadays, because of our advent of electronics, people are going one step ahead and transmitting these signals as voltage mode, but modulated, and digital communication techniques are being used for this communication, which are also very robust to noise, but which also offers you various other benefits, such as a very high bandwidth channel, simultaneous transmission of several variables over a conductor, etc. we will see these things, some of these things towards the end of this course in the industrial, when we look at the industrial communication systems. So this shows that current transmission is much more robust to series mode interference. This again shows that common mode interference appears as E Thevenin plus VCM and VB equal to VCM. So as I was telling, that if you take a differential measurement and feed, then the voltage across it is still E Thevenin, but if you make a single ended measurements from this point A, then the whole of common mode noise source which is here will actually appear. So this shows that why differential measurements are better. Now we are coming to electrostatic coupling. So in electrostatic coupling, what happens is that there are always, whenever we have conductors, there are always capacitive couplings between conductors. So this is the power cable which is possibly at a very high voltage, and this power cable, there is a capacitance to the actual signal lines. Both signal lines there are capacitive couplings to the earth plane. So now you can understand that especially if this C1 and these ratios, that is this C1 to C1e and C2 to C2e are different, then you are going to have a good amount of voltage induced, and especially if this voltage is, if it is an AC, then current will tend to flow through these capacitances, and naturally at the capacitor divider point some voltage will be induced. So this is the phenomenon of capacitive coupling, through which a high voltage conductor can induce noise voltages into your circuit. So one of the ways of circumventing that, or rather overcoming that, is to make a screen. So if you connect it by a conducting screen and then connect the conducting screen to earth by a solid connection, then what happens is that there is now no direct coupling between because this whole screen is actually at ground potential. So this is actually connected to ground through this solid connection. So what happens is that these capacitances are independently connected to ground. So you have this connected to ground, you have this connected to ground, you have this capacitance connecting to ground, and you have correspondingly you also have these connected to ground. So these capacitances, so the voltages here do not cause any voltage into these signal lines. This is the principle of screening. Similarly, you can have a similar principle where you have shielding, and sometimes in electronic circuits, especially when there are very high impedance, very susceptible points, typically the amplifier inputs, where if you have a small signal, because of the very high gain of the op amps, a large noise component will arrive at the output. So such sensitive points in the circuit, like the op amp inputs, are sometimes connected by what is known as a guard ring. So these are all to reduce electrostatic coupling with external sources such as power supply voltage or even other sources. And then, so these are, in a way, these are preventive mechanisms which ensure that less noise gets into the system, but some noise nevertheless will get into the system, and after they get in, the other way of removing noise is by using filters. So filters, as we have seen, we have studied it in the last lesson. So filters are frequency selective networks, and they will, so if we can design them cleverly, and if we know in which frequencies noise is there and in which frequencies signal is there, typically if they are well separated, then we can separate out the noise using filters quite well. Another very common kind of noise which arises in instrumentation is due to sampling and quantization. You see, typically, finally, in modern instrumentation systems, we tend to get the signals into computers and then use them in various kind of processing, digital control, etc. So what happens is that sometimes sample and quantization errors can come in, although these errors are gradually becoming more and more small, because of the fact that the speed of electronics is increasing manifold. So you can easily obtain very high number of samples, and secondly because of the fact that the number of bits which are used in processing are also becoming quite large. So the quantization error, which is typically limited to to this plus minus half LSB kind of specification, sometimes you see that is because of quantization. Now this the weight of the LSB becomes very small, and so therefore these errors can be sometimes neglected. So generally speaking, these errors are gradually becoming more insignificant. So now we have taken a look at noise, and now all these finally contribute to what is known as measurement error. So measurement error can be contributed by various things. For example, measurement error can be contributed by noise sources. Measurement error can be contributed by external environmental changes, like change in temperature, like for example in a strain gauge. There may be another input, that is the transducer itself may be sensitive to not only the desired input, it may be sensitive to other factors which may change. It may arise due to improper methods of measurement. So for example, if you are measuring temperature using a thermocouple, and if you are not making the ambient error correction, then you are going to get a cold junction compensation, then you are going to get an error. So errors can come from different sources. They may be internal or they may be external, right? Similarly, they may be external causes that introduce unwanted signals or affect system characteristics. Sometimes for example, especially if you have a Wheatstone's bridge, if the supply voltage to that bridge changes, then the whole gain of the bridge will change. That is, if the output voltage, suppose we are trying to sense resistance change. So the sensitivity between output and resistance change is dependent on the supply voltage, as we have seen in the earlier lesson. So if the power supply voltage of the bridge changes, then immediately there will be a gain change in the instrument. So the system characteristics is changing. So such things can happen, or there may be sometimes they may arise due to internal causes, like internal noise, etc. Or sometimes they may arise due to model simplifications. That is, we assume that something is linear. For example, platinum RTDs or nickel RTDs more pronouncedly. If you assume them to be linear, then because you have simplified the model, actually they are not linear over the temperature ranges. So because you are using a simplified model, so there you are going to get measurement errors. That is, the measured value that you are reading may not be equal to the temperature. So, but we have to be very careful we have to have a clear understanding about these errors, their bounds and their nature, because unless we do that, we don't know if we don't know the quality of these values which we are using in control purposes, then as we have said, that among other things, our product and process qualities will suffer. So it is important to, for example, this is a typical way that the input output effects in a measurement system are captured. So you have, in this case, there are three kinds of inputs. This is the desirable input. So you want to see the variation of the effect of the variation of this on this output. But there are other kinds of inputs which come in. For example, this modifying inputs which change the characteristic of the instrument. So for example, gain change, that will be a modifying input. So the change in the supply voltage will be a modifying input. Or let us say the gauge factor of a strain gauge itself is dependent on temperature. So that's a modifying input, because it changes the relationship between strain and resistance change. Similarly, there are interfering inputs. So for example, in a in a thermocouple the ambient temperature is going to be an interfering input which gets added, you know. Even the same temperature can be an interfering input, like for example in the case of the strain gauge, the temperature changes the gauge factor, so it works as a modifying input. It also causes a resistance change which is thermally induced by the thermal coefficient of the resistance, so that is an additive error, in which case the same ambient temperature is actually acting as an interfering input. So in other words, there are several modifying and interfering inputs, and for example, and we capture the output finally as, you know, so this is the main path. So we say that in the ideal case, you can forget about this dynamics for the time being if you only consider steady state readings. Then the output is actually ki, this is not 1, this is I, so ki plus A. Now along with that, if you have interfering inputs, then it is going to be ki plus A plus k1 I1. This is the effect of the interfering input. Along with that, if this k itself gets modified by a modifying input, so if k changes to k plus km im, where the gain itself is getting changed, then you will have another term which will be k plus km im into I. So that is the other term. In other words, then also there can be, this is ni. So in addition there can be some nonlinearity effect. So for example, if you are going to make a very accurate measurement, then sometimes you put in those nonlinearity effects, and you can say that in this temperature range, in that temperature range, use such polynomials for temperature to resistance variation. People use that. So this will probably give you a much more accurate behavior of the instrument, and note that these are so when we use such a model, we are actually trying to model the effects of these modifying and interfering inputs, and thereby we are trying to compute the response in terms of these inputs. But even apart from them, there are going to be some unmodeled effects, you know. Ambient temperature variation may be measured. If it is measured, and if its sensitivity is known, then it becomes a modeled effect, and we can take it into account while we are interpreting the measurement, interpreting the output. On the other hand, if it is left as an unmodeled effect, you are not measuring it, you do not know it, then you can measure it as a random signal, and you have to express it in terms of only bounds. So you can say that the instrument will be plus minus 1% accurate if it is used within this ambient temperatures. So you are not interested in quantifying the value. So measurement errors are classified accordingly in two ways. One is, it's called a random error. The random error captures all the effects which are not modeled. So you know, some signal is getting coupled through from some power line. You actually may not be able to model it, because especially if it's a portable instrument, you are moving it from here and there, you don't know what coupling exists when you are making a measurement. In such a case, it will be a random error. And there, on the other hand, there may be some systematic errors which are sometimes called bias, so which can also affect the measurement. Random errors are typically specified by specifiers. So error sources can be electronic, or as I said, unmodeled internal causes, unmodeled external inputs like temperature if you don't model it, and they are generally characterized statistically. So you say that the unmodeled error has this kind of a mean. So the error has this kind of a mean. Normally the mean of the error you try to characterize as a systematic error, which may be in terms of variations of temperatures, etc., and the random part of it you typically characterize by a zero mean statistical distribution, which is often assumed to be Gaussian. And these are random errors are reflected in the precision or repeatability specifications. So you see that this will probably clarify the picture that the true value is here, the measurement that you are getting is around this point. So every time you are going to make a measurement, most probably you are going to get a measurement between these two values. So the mean of this, so this part is your systematic error, and this is your variance or spread of the random error, which you typically express in terms of a standard deviation value. So one has to understand these specifications, so these the systematic errors are often classified, often even quoted by manufacturers in terms of quantities like gain error. So this is the mean. Oops. So this is the mean and this is the variance, standard statistical distributions definitions. So systematic errors are those which can be modeled in terms of effects other than the measured, or so effects other than the measured, so modifying and interfering inputs, measurement, or in terms of nonlinearities. Sometimes nonlinear, sometimes we want to simplify a model, we want to use the instrument simply. So even if we know that the instrument is nonlinear, we sometimes say that it is going to be linear with this much kind of error within this accuracy levels. That is sometimes a simpler specification to use rather than going through nonlinear functions. So error sources are interfering and modifying inputs or nonlinearity errors. So in such a case, such errors, such systematic errors, sometimes you try to characterize as, very often you try to characterize in terms of a zero offset and a gain error. So this is the, so suppose this is the anticipated response, that is the instrument is supposed to be have a nicely go through 0 and have a sensitivity, but actually what you observe is this. So this error you actually classify in terms of a 0 offset and a sensitivity change. So you say that it is going to be within so much plus minus 0 offset and within so much, so the signal is going to be within, while you are actually assuming that the ideal response is this, the signal is going to be like this. So in this way sometimes the systematic effects are quoted in instruments and they are interpreted. Lastly, so this deviation from non-linearity, while it is a systematic effect, sometimes we don't, if we put it as a systematic effect, sometimes we don't put it as a systematic effect, but rather put it in the error and then try to quantify it, that what is going to be the maximum deviation from non-linearity, because we don't want to, because we want to avoid the complexity of the non-linearity in the regular usage. So now what we are going to see is that normally, as we have seen, that measurement systems are one after the other, there are several blocks, each of these blocks can have various kinds of characteristics, error characteristics. So if they are connected in series, then what is the overall error characteristic of the instrument? So how to calculate that? So you see that, let us first characterize the mean characteristic. So you see this is a block which has an I1O1 characteristic, which may be given by this one. This is the I1O1 characteristic of the first block. Now O1 is acting as I2 of the second block, and there is an I2O2 characteristic of the second block, which is this. So in this second block I2, you are going to put I2 is equal to O1, so O1 is this. Now when you will calculate I3, that will be equal to O2, and O2 in O2 you will have a characteristic of I2O2, where for I2 you will put this one. So in this way, if you put the mean values of these nonlinearities, and if you know these effects, then you can calculate what is the mean values of the element output. So in this way, the mean value can be combined if we have the characteristic, mean characteristic of the various instruments. On the other hand, the randomness of the whole so on the other hand, if you can also combine the standard deviations of the various individual blocks to calculate the overall standard deviation of the output of the whole instrument. So which is very similar, and which assumes that the randomness effects which actually occur in the various components are actually uncorrelated. That is an assumption which may or may not be always valid. So if we do that, then this is a very standard rule of statistics, that if you have the gains, you actually multiply the individual standard deviations by their corresponding gains, and then you get the standard deviation of the output. So, here you are expecting the standard deviation of the output in terms of the standard deviation of the various inputs which affect that input output block, and then you are using that as the input standard deviation and again putting in the second block. In this way you are going on substituting, and finally you will get the standard deviation of the output. So, this is the way one can find the random specifications of an overall instrument. So, here is a small example. So, you have a temperature measurement system in which we are only looking at the recorder. So, you see the recorder has a model equation like this. So, we say, suppose we say that individuals, that the gain k does not vary, it is very well known, while a and sigma I actually can vary. The partial derivatives are easily calculated. This is the mean value of the gain, this is the, here it is 1. So, the overall mean value you can easily calculate, it is k bar I bar into a bar, and the overall standard deviation also you can calculate. So, you can find out that if the manufacturer gives the specifications for these if you can calculate, then you can calculate the overall specification, overall random, the standard deviation of the output. So, we have come to the end of this lesson. We have studied, basically we have studied noise coupling mechanisms, and we have studied the some basic thumb rules of noise reduction, and then we have studied the characterization of measurement error and its propagation. So, in points to ponder, there are, for example, you can try to figure out 3 typical causes of electromagnetic interference in the industry. I can tell you that one of them can be brushes of DC motors. There are all sorts of DC motor drives in industry. So, if the brushes are loose, then there is going to be some sparking. So, that is one of them. You can think of other causes of such electromagnetic interference in the industry which can occur. Then, why are high impedance points in circuits vulnerable to noise, and what is the remedy? So, why they are vulnerable to noise, you can understand if you can find the impedance from the noise source to the ground through the coupling path. So, if that point has a high impedance to ground, then you can see that what amount of voltage will be coupled compared to if it is a low impedance point. The remedy we have already discussed in the lecture. Why are earth lines and planes in circuit PCBs made of large areas? We have also discussed. You will typically find this. Name a current transmission standard which is very well known, right? So, you can try to also figure out that why it is called like that. And finally, you can try to ponder over this idea that systematic errors can be corrected for by calibration, but random errors cannot be. So, justify your contradiction. So, we come to the end of this lesson. Thank you very much. This is also the end of the module on instrumentation. From the next module, we will start on process control. Thank you very much.